Yes, time to start. Unmute. Yeah, now, chaotic technology. Time to start. Today we have, oh, now we lost.
Yeah, something is happening now. Stop it because the external display is disconnected. Should I share again?
Yeah.
This one, I think.
No. Oh, it should be this one, but we.
This?
Yeah, this, okay. And then you need to restart this one. Let's try again. So we have Isaac Sanchéz dissertation today, and we have part from Isaac. This work has been done with me as supervisor, Mattias. We have Irida Shalari, that is the co-supervisor. This work has also been done in close cooperation with Axel Jansch at the Technical University of Vienna. For this defense, we have 4 important persons. We have the opponent, Johan Lilius from Akademi in Finland. We have Gustafsson from Linköping University. Then online, we have Per Gunnar Kjelsberg, NTNU in Norway. And then we have Francesco Bonavolontà in Naples, Italy.
Naples, Italy, yes. Yeah. Yes.
Thanks. So the procedure today for this defense is that Isaac will present his work, roughly 35 minutes.
Mm-hmm.
Then we will have a short break where we will disconnect the YouTube broadcast. After the break, we will continue, and then we have the opponent that will lead the discussion. When the opponent has asked all his questions, we move on to the grading committee to ask questions. And when the grading committee is finished, we move on to the audience. So the floor is open to ask questions. When the public part of this defense is ended then, the grading committee, opponent, supervisors will go have a closed meeting where the grading committee will take the decision. At the same time, you in the audience can go to the 3rd floor and wait on us there. And now it switched again.
That's okay? Or?
Yeah. And then you need to redo what you did.
Maybe I should share also?
Yes.
And restart.
Yes. So, then we have come to the part where you can start. And before you start, it's also the question if you have something that you want to add to your thesis or...
No, I think I don't want to add anything.
No. Then.
Okay, so good morning, everyone, and thanks for joining. Today, my name is Isaac Sanchéz, and today I'm presenting my doctoral thesis in electronics that is titled Partitioned Deep Neural Networks Inference on Resource-Constrained IoT Devices. This work was developed under the supervision of Professor Mattias and Dr. Irida Shalari. To understand the motivation behind my work, let's have a look to the global context of IoT trends. In 2020, there were 11 billion of IoT connected worldwide. This amount is projected to reach around 39 billion by 2030. This growth is coming with a high demand for intelligence applications, where computer vision allows these devices to see and understand their surroundings. This enables mobile applications, like the inspection of factory floors, the use of autonomous wheelchairs to assist patients, or infrastructure monitoring. All these applications operate on batteries, and their hardware has limited resources. And this leads to a fundamental conflict. On the one hand, computer vision systems are based in deep neural networks, and these algorithms are starving for energy and computational resources. On the other hand, we have IoT devices, the one we want to make smarter. They are tiny, battery operated, and weak. So there is a mismatch between the computational demands of DNNs and the limited resources of IoT devices. So the question is, how can we fit this very big range in such tiny and constrained devices? There are some common approaches for DNN implementation. For example, the use of efficient hardware to attend the demands of DNNs. Or we can just try to apply tiny machine learning techniques to compress the model and relax those demands. Or we can, for example, apply node offloading to relax also the demands. Focusing in deployment strategies, there are three options to deploy a DNN. We have everything on the node, that is saturates the hardware. We can move the computation from the node to the server, so we just send the image. Or we can apply partial node offloading. That is the focus of this work, what we call intelligence partitioning. This strategy splits the DNN in two parts. One is implemented in your node, and the other in the server. However, this strategy introduces a new energy cost in the node, that is communication. And this implies that to save energy, we need to understand the trade-off between processing and communication very well. If we have a look to this trade-off for traditional systems, as we process, we reduce data. And when this happens, the communication gets cheaper. That's why we are able to observe an efficiency valley to locate our optimal partitioning point. On the other hand, moving to DNNs, when we process data, we expand data. Then the communication gets so expensive. Now, we are able to see this efficiency valley. So it's not obvious where to split this kind of systems. The question is, how others are addressing this problem? Let's have a look to the related work. Some works use orchestration strategies. They optimize where to compute. The main problem here is that many of them don't compress data. So the communication gets expensive and makes partitioning infeasible. Also, they face very accuracy speed trade-offs. Or they just compute everything in the node and they overload the node. The second group of works know that communication is a problem. So they apply lossy compression strategies. The problem with this is that they are destroying the data. So this has a global impact in the accuracy. The third group of works use neural encoders to compress data. The problem with this strategy is that they are adding computational load to the node. Others just put these encoders at the beginning of the architecture to compress the input data, but they erode the data. And this has also an impact in the accuracy. So based in this analysis, I'm detecting three main problems. The first one is about shifting or adding computational load to the node. This increments the energy cost and complicates the node scalability. The second is that current works reduce the data with lossy compression, and they don't have a mechanism to regenerate this data. And the third one, focusing the optimization efforts. Every single optimization action at the node has an impact in the global accuracy. If we put everything together, there is not a methodology that covers all these aspects. So the research mission is design a unified methodology for efficient node offloading without compromising accuracy of DNNs. To achieve this mission, I'm formulating 3 research questions. The first one relates to the trade-off between processing and communication. We need to understand this very well. And I'm doing this from the, sorry. It looks like there is a problem. Let's go directly to the slide. I think there was a communication problem, and that's why we need to reduce data. So yes, the first research question starts from input data. So how does input data system efficiency impact system efficiency, and how can this interdependence be used to guide design exploration in distributed DNNs? The second relates to the actions we need to split DNNs. How can efficiency be induced at intermediate partitioning points that are otherwise non-viable in standard DNN architectures? And the third one relates to the accuracy. How can accuracy preservation be ensured relative to the baseline accuracy when applying the transformations required to induce efficiency at an intermediate partitioning point? To answer these questions, I rely on this analytical performance framework that starts with an assumption. Sensing energy is constant. With this, we are able to isolate the most important variables, energy and latency. For energy, we refer to the energy at the node. It's where we have limited resources. And this is compounded by processing and communication. For latency, we refer to the system latency. That includes all the latency due to the node, and also we are adding latency at the server. That includes the processing from the partitioning point until the output. This model helps me to isolate parameters that I want to evaluate globally. So armed with this framework, we are able to move to the first phase to answer how to use system independence to predict partitioning configurations. In this first work, I evaluate the impact of input data on it. Sorry, there is a problem. Yes, okay, solved again. In this work, we want to evaluate the impact of input data on partitioning decisions. What we do here is generate a dataset that varies in 2 dimensions, image content and resolution. We want to know what happened with these two variables in the energy and latency. So what we do is evaluate what happened with energy and latency at these partitioning points. The results show that the optimal partitioning point depends on image resolution and not the content. And this is because in a processing pipeline, almost all the most tasks at the beginning of the architecture are processing pixels. Only the remaining ones at the end process objects. So, for example, for this example, where we are using the communication technology LTE category 4, for this specific image resolution, when we increment that resolution, the partitioning shifts deeper in the architecture to the partitioning point 9. We found a causal chain, that is, when we increment the resolution, we increment the data volumes between the tasks. So this affects the number of operations and also the data volume. As a consequence, processing, energy, and communication increase. And the impact is this. The partition shifts into, deeper in the architecture. From this work, we are able to detect the main two parameters that affect the trade-off in processing and communication: number of operations and data volume. And we use them in the next work. Here, we develop an analytical model to identify processing areas that deserve optimization efforts. The methodology is this. We extract the number of operations and intermediate data volumes from our system. We calculate mathematically, it's an estimation, the processing energy and the communication, and then we feed these values to our analytical model. Objective, to find that points that minimize the energy. For this work, we are testing 4 systems, 2 traditional image processing systems and 2 CNNs. So we have people counting scenario, particle detection, BGG19 as a convolutional neural network, and AlexNet. The results, here in the results, you can see the possibilities of the partitioning points for each of the systems. In the current graph, we have people counting with the communication technology Bluetooth 5. The optimal partitioning point for this case is the number 2. Moving to the next traditional system, particle detection, modifying the communication technology to LTE category 4. Now the optimal partitioning point is the number 4. If we move to CNNs, we can see that the optimal partitioning point is the number 1. And this is sending the image at the beginning, no partitioning point. And if we move to AlexNet with LTE category 4, we have the same problem. We tested 9 communication technologies, and any of them, deploying again, yes, we tested. What happened? No. It's open, yes. Yeah. No, it's not PowerPoint, no. Let's open this again. So, yeah, let's continue and see what happened. Sorry? It's not shared. Can you see the screen sharing has stopped? Yeah, there is an issue. Mm-hmm. I'm gonna share. Can you see? Or, but not here. Mm-hmm. Yes. Mm-hmm.
And we share this screen instead. This share.
Sorry.
I'm not sure. Press play.
So we start from here.
We
Yeah.
try this one?
Yeah, we try. Yeah, let's see. No.
No? Okay.
No. You can see in Zoom? Oh, no, now it's coming back. Okay, yes, sorry for these difficulties. Okay. Yeah, something with the screen. So, yeah, so you continue, I think. Okay, so we tested this experiment for 9 communication technologies, and the results were consistent. Standard partitioning is inefficient for CNNs. Let's pass this again. Yes, so now at this point, we are able to answer the research question 1. Should I continue? Yeah, okay. And splitting the research question in 2 parts, how does input data impact system efficiency? It does through the resolution that scales both processing and communication. How can this interdependence be used? So we use this with the number of operations and data volume to enable to predict efficient partitioning configurations, where the main outcome is that DNN exposes a structural barrier that makes offloading inefficient. Now we are ready to go to the next phase, where the question we want to answer is, how can efficiency be induced at partitioning points? From the previous work, we observed that there is a structural barrier that is preventing DNNs from offloading. So it's very logical to compress data at the partitioning point in order to reduce the communication cost. And the expected result here is to induce a new optimal partitioning point. For this work, I'm focusing in object detection tasks, specifically to detect fit. And I'm using TinyYOLO version 3 as a convolutional neural network. I'm contemplating 3 scenarios. The first one is computing everything at the server. Here we compress data and we send directly to the server. The second one is computing everything at the node, local inference. And the third one are 5 partitioning cases. To select potential candidates as a partitioning points, we follow 3 steps. The first one is focusing in sequential paths only. In this way, we avoid sequential synchronization problems. Also, we focus in early layers to avoid the processing energy accumulates. And we focus on that points that provide low data volume to reduce communication. At the partitioning point, we integrate our wide data reduction pipeline that has 3 operations. First, we quantize data to reduce the information. Then we pack the data to reduce the size of the data. And then we apply C compression to remove the last redundancy in order to compress a bit more. We apply 2 kinds of quantization methods. The first one is a variant of min-max normalization. With this method, we distribute the quantization levels equally. But there is a problem. When we reduce the precision of quantization, this distribution starts to be unfair. And this is because the data distribution sometimes are not symmetric. So we have most of the data as 0 and the rest as 1. And the neural network is not able to generate a proper future map that the CNN can understand. For the method 2, that's why we applied the second method that is more fair, splitting the data distribution. This is based in the mean average in the mean value of the data distribution. So as you can see, now the CNN is able to generate this feature map that is keeping some structure. The method I'm following, the experimental workflow, follows 6 steps. First, we train our initial neural network, the YOLO. Then we insert our wise tightening data reduction pipeline. Next, we separate the server part and we fine-tune that to let it know that there are new data, new features that are quantized. Then we split the model and we integrate one part in an I/O node and the other in a server. And finally, we measure energy and latency and we evaluate. Here are the results. In this first graph, the objective is characterize the evolution of the accuracy and data size when we reduce the quantization precision. So you can see here I'm plotting 2 results. The first one is for quantization method 1, where when we reduce the quantization level, we reduce the information and the data size, and then the accuracy drops. We have this cliff effect. For quantization method 2, we have 5 isolated points because we are just evaluating 1-bit quantization. As you can see, they are keeping very good accuracy even with only 1 bit. And this is because this quantization method is able to distribute the values better. From this experiment, we select the best cases that are the ones that minimize the data size and maximize the accuracy. And we plot this latency energy graph. Here you can see that the 3 cases, all in server, all in node, or 5 partitioning cases. The best design case was the partitioning number 1. And it is 2 times faster than the solution with all in server, but also we are achieving almost 4 times energy saving comparing with all in node. To understand the results, I'm having a look to the feature maps. And I detected that many of them were turned to 1 value. So they were almost null. They provide no information. And that's why we are able to reduce the data by 20 comparing with the initial feature maps. The question here is, if some feature maps are useless, why do we compute them? And this brings us to the next work, where the goal is enhance data compression and improve the communication efficiency. So the strategy is apply pruning to detect first those feature maps that are almost null and prune them. And prune the filters that generate them. This is the expected result. After pruning a filter, the feature map just gets totally null. And then the packing and compression do the rest of the job. With this, we expect reduced communication communication costs. We are applying pruning in 2 steps. First, we prune the partitioning layer where we have these null feature maps. Then we realize that maybe we are using other filters to compute those null feature maps. They are contributing to that solution. So we detect them and prune them also. So we prune backwards also, all the node. We don't detect the null feature maps manually. We apply a magnitude-based method to identify and prune those redundant filters. Here are the results. On the left, results from the previous work, where we apply just quantization, where the best design solution was the partitioning number 1. On the right, we have the solution for this work, after quantization and pruning. The first thing that you can see is that if we compare partitioning ones, we are reducing the data even more. But now, the best design solution is the partitioning point number 4. So we have the same effect that for traditional systems. The partitioning point is shifting deeper in the architecture. But let's have a look to the quantitative results. If we compare with all-in node, now we achieve by 17 times energy saving. And we are accelerating the system 5 times. To understand the results, I'm plotting these conceptual graphs. Here we have the result, the conceptual result from the previous work. We apply quantization, and we just induce an optimal partitioning point. Then we prune the partitioning layer. Thanks to this, we are able to reduce the data by 250 times. Thanks to that, we reduce the communication cost. By pruning the rest of the layers at the node, we reduce also the computational load. And as a result, we have our new optimal partitioning point that is even more efficient. It's faster, it provides a better speed, and at a lower cost. Then we are able to answer the research question 2, that was, how can efficiency be induced at intermediate partitioning points? So the answer is applying a co-design strategy that involves both quantization to remove the communication barrier and make data transfer more efficient, and pruning to enhance the compression and also the communication. The main effect here is that also we reduce the computation. But not everything is perfect. We reported accuracy drop between 3 to 10 percentage points. And this leads us to the next work, where the question is, how can we restore the accuracy? From previous works, I tried 2 different methods to try to restore the accuracy. The first one is about lowering the compression. So the problem is, if we are losing information, why not to try a higher quantization level, like 3 bits, for example? But that sacrifices efficiency gains. Our optimal partitioning point disappears. Then I try retraining the server part. So it's aware that quantization is happening. But this has limited recovery. So looking at the feature maps, I realized that the quantization method 2 was keeping the data structure very well, and this was a repetitive pattern. It was systematic. And when something systematic is learnable. So I proposed train a supplementary neural network to reconstruct the fidelity of the original feature maps, the ones before quantization. Let's have a look to this visual concept. We have our quantized feature map, and we want a representation that is closer to the original one, but it doesn't have to be the same, but rich enough in order to make the CNN to understand the computer vision task. Here's how can we implement this. This is an example. We have our neural layer, neural network model. We split it. Then we implement it in the node and the server. We introduce our data reduction pipeline. And then we implement our QCNet quantization compensator neural network that is in charge of reconstruct data. QCNet resides entirely in the server partition. So this means that the node is handling a very simple compression operation. And the server partition is in charge of a very complex reconstruction operation. This asymmetric architecture enables node offloading. And this is what we want. I tested 3 different architectures for the QCNet, based in convolutional layers, based in transpose layers, and transformer based. But at the end, I selected a hybrid combination between transpose and convolutional layers. I call this edge QCNet, hybrid QCNet. To implement the QCNet, we follow 2 steps. First one is train it separately. It learns to reverse the noise. Then we integrate it in our host model, and we fine-tune only the server. So it understands there are new reconstructed features to understand. For this experiment, we extended our scope, including more neural networks, like ResNet 50, a Vision Transformer, a ComNext Tiny, and also we are expanding our case with YOLO. In addition to detection, now we are including classification and using more datasets based in ImageNet. Let's have a look to the results. The first experiment is about validating the QCNet, the architecture. So we integrate it in 3 neural networks, in ResNet, Bit Transformer, and the ComNext Tiny. The blue bars indicate that the baseline accuracy. After integrating our data reduction pipeline, the accuracy drops until the red lines. And then when we integrate our QCNet, the accuracy goes up again until almost reaching the baseline accuracy. To the right, you can see the architecture for the QCNet for the Vision Transformer. In the next experiment, has 2 objectives. Compare. First, we want to expand our YOLO case. The blue bar indicates the baseline accuracy, and the pink one, the accuracy after we implement our QCNet. As you can see here, we are overpassing our own results, reaching almost the baseline accuracy. Comparing with latency, our QCNet is 2% slower. This is because we are shifting burden to the server. But the server is powerful, I can manage it. So it's only 2% slower. Now, comparing with an autoencoder-based solution, we can see that we are overpassing also the accuracy results, but also reaching totally the baseline accuracy. And comparing the latency, we can see that we are 7% faster now. And this is because the autoencoder solution is shifting the burden to the node, and that's not efficient. They have to pay the bill. Let's have a look to qualitative results. Here I'm plotting the similarity graphs that tell us how well is the QCNet reconstructing data. The green distributions are comparing the original future maps with the quantized ones. And the blue distributions are comparing the original future maps with the reconstructed one. For the Vision Transformer, we can see that the reconstruction is successful. It's very high. So the future maps are very close, are very similar to the original ones. The same happened with convex tiny. But when we go to ResNet, we see something different. The reconstruction is not successful at all. Yes, we are reconstructing data, but the similarity score is very low. It's only 0.45. So why this is happening? So then I checked what happened with the future maps. I observed 2 primary mechanisms, reconstruction and regeneration. When the quantization keeps data structure, the QCNet is able to fill the details and reconstruct data. When the data structure totally collapses and we have a null future map, the QCNet is regenerating this future map. So it's creating a new one. It looks like the QCNet is taking advantage of the neighborhood features and filters to generate a new viable future map. to observe if after the reconstruction, the neural network is able to focus the attention in the same area, for example, to detect glasses, I'm plotting these semantic retention future maps, where we can observe that before reconstruction, the neural network is focusing in the nose and eyes. And after reconstruction, also is focusing there. Now we are able to answer the research question 3. How can accuracy preservation be ensured? The answer is that we cannot preserve the accuracy if we apply extreme optimization actions at the node. But we can recover the accuracy globally by reconstructing data. On the right, you can see how we close the case for YOLO. Before reconstruction, the neural network is focusing the attention in the legs and the feet to detect the feet. And after reconstruction, with the QCNet, it's focusing in the feet. This is telling us that after reconstruction, the QCNet is able to keep the spatial information that allows complex applications like object detection, where the spatial information matters. To conclude this presentation, I would like to highlight some the key contributions of this work. I proposed a system-level methodology to allow the partitioning of DNNs. This involves 2 stages. The first one is efficiency induction. Here we apply our optimization actions, quantization and pruning. Then we have the compensation stage. We compensate for the error introduced. So we reconstruct data to restore the accuracy. Thanks to this induction compensation mechanism, we are able to relax the trade-off between hard optimization and accuracy. As a future work, I think it's very interesting to automate the design flow involving this work, like, for example, the generation of the QCNet or the optimization efforts. Also, I think it's very interesting to try something new, like the use of a binary neural network as a head model in order to bypass quantization and pruning. In addition, today we are testing adaptive partitioning strategies to adjust the compression to the bandwidth conditions, because we don't always need to compress as much as possible. Also, we want to extend our scope, applying our methodologies to large language models. And with this, I conclude my presentation. Thanks for listening. Thank you.
Thank you, Isaac. Then we will have a short break before we go into the questioning part. How many minutes do you need to? 10 minutes, and we'll resume.
Thank you, Isaac.
Thank you.